just double check here that we're live.
Yep.
Okay. Why are we not live here? One moment. And we have 36 participants in this Zoom. Welcome, everyone. And as you're joining today, let us know where you're tuning in from. Okay, we are live on YouTube, and we're just waiting on LinkedIn now. And if you are in today's Zoom or YouTube, you are tuning into the Delta Lake Deep Dive, streaming Delta Lake with Apache Spark, structured streaming. And I see hands are already being raised. This is such a hot topic. Any questions, please place in the chat. Okay, and we are ready to kick things off today. We are live on LinkedIn and YouTube, and we're in here on Zoom. So good morning, afternoon, evening, everyone. Welcome to our exclusive webinar. This is a Delta Lake deep dive, streaming Delta Lake with Apache Spark structured streaming. My name is Carly Akerley, and I will help facilitate today's conversation. I am a communications manager at the Linux Foundation. Today's session is tailored to broaden your understanding and enhance your skills in the world of streaming Delta Lake with Apache Spark, all about that structured streaming. And I am very excited to introduce our speakers today. We have Bartosz Konieczny and Scott Haynes, whose expertise and experiences will be perfect for today's webinar. Bartosz is a freelance data engineer who's been coding for 15 years. He's held various senior positions that has helped him get through the data engineering problems in batch and stream processing. He also enjoys data challenges and has a blog, which he actively uses, waitingforcode.com. And we also have Scott Haynes, a distinguished software engineer at Nike, a Databricks beacon, and he's also been working in data-intensive, highly distributed systems for the past 15 years. He is also a published author, and he'll touch on that a little bit more later in today's session. As we delve into today's topic, we encourage you to engage with our speakers. Feel free to ask your questions, share insights in the chats wherever you're accessing today's webinar from. It's not just a learning opportunity, but this is also a discussion and exchange of ideas. And without further ado, I will pass the conversation over to today's speakers. Thank you.
Yes, thank you, Carly. Hello, everyone. So let's get started. We are going to talk today about Delta Lake and Apache Spark structured streaming. So as Carly introduced, my name is Bartosz Konieczny. I'm a data engineer. I'm blogging at Waiting for Code, and currently I'm focusing on stream processing for almost 2 years already. And I'm also working on a secret project. I hope I will be able to talk a bit more on that in a few months. And we can connect on LinkedIn, or if you have anything to share or to ask, I have an email. I will try to answer as soon as possible, but there's some other deadlines. So please be patient. And I'm today with Scott.
Oh, yeah. Me. So I'm Scott Haynes. Bartosz, thanks for also setting all of this up and just getting this thing to happen. Let's see. I've been in the Spark community forever, and Delta Lake community since 2018, and just been enjoying the ride since then. And we're excited to be part of this conversation today. Back to you, Bartosz.
Thank you, Scott. And the first things to understand is why this talk. So I think we are all aware of Delta Lake capabilities for the batch processing, for the network querying, for all this great stuff you can do with time travel and things like that. But this streaming part is a little bit hidden, and we think less popular than the batch ones. And we wanted to share a little bit with you what we can do with streaming, and maybe why not encourage you to start writing your first streaming pipelines with Delta Lake structured streaming or Apache Flink, because Flink is also another connector available for streaming on Delta Lake. But we'll focus here on structured streaming only. And we divided this presentation into two parts. I would say, let's say the easy one and the hard one. I will start with the easy one that will cover some basics about reader and writer APIs, and also some gotchas you can encounter as a consumer. And later Scott will complete this picture, this kind of simplistic and optimistic picture, but some hard stuff about schema enforcement and schema revolution. But no worries, I think it's hard because I'm saying that, but after Scott's explanation, it will be much more approachable and you will be able to work on them despite these difficulties from the beginning. So what does it mean streaming a Delta table? Here you can see two places. We have our Delta table at the bottom, and at the top you have kind of general steps that are present in Apache Spark API for interacting with the Delta table with the streaming semantic. And everything starts with the Spark source init, where the job retrieves the most recent snapshot and keeps mostly for the schema purposes, because schema is kind of sensible topic for Delta Lake, and you will understand it better with the Scott's part. But I will keep this sample here. And next part is to define what you want to do when you want to start. And there are three choices. You can either do some time travel with version or timestamp, or you can decide to read the most recent table version. And this is a little bit tricky. At least when I started to analyze this fact, the streaming with Delta, I was like used to working with Kafka-like data sources, so the change logs. And in Delta Lake, for example, when you don't define any starting version and you have some updates, when you start your query, you will always get the last version for each row. So that's a kind of the first difference you may encounter while we are switching from these streaming broker systems to Delta Lake and to streaming on Delta Lake. The second step is to define how much we want to take for each micro batch. And here you have three choices again, but the last one is not really a choice. So you can define either the number of bytes, the max files, or by default, the rate limitation is of 1000 files. And among the catchy things here is that the max bytes is really the max number. It's not anything exact. Apache Spark will analyze the commit log, the size which is associated to each added file in the commit log, sum them up, and sum them up as long as the sum doesn't reach the threshold you defined. And the second tricky, but it's maybe me, I was like thinking about this more in transactional scope. I was like thinking that the max number of files you define are transaction aware. So let me give you the example. If you have five created files in each transaction and you want to read, for example, up to 7 files, Delta Lake will either take the 5 files from the first transaction or 10 files. So it will also blurry this definition a little bit. But turns out it's a much more easier. Is the exact number for the lines the added files you have in the commit log. And at this stage, we have all the metadata which is required to build the data frame. We have all the added files, we have the first and the last offsets. And the next step is quite important, is already the schema validation. So I'm spoiling a little bit the Scott's part, but there are additive and non-additive schemas. And at this moment, if your schema is not compatible, so for example, when you have done some non-additive changes like rename or drop, your query will simply not start. But let's suppose that it didn't happen, and in the next part, with all the information you gathered before, you create the data frame directly from the files that are present in the commit log you loaded, and from that you can start processing the data. So that's quite easy, but when you deep dive a little bit, you will find the first, I would say, surprising parts, and mostly to start with the checkpoint location, the checkpoint files. Already you can see that we have kind of different naming here. We talk about the reservoir, and in fact, it points out to the table ID, and Jacek Laskowski in his Git books explained why. So he's kind to put it short, it's a legacy name for Delta, the legacy name used for the tables in Delta Lake in the beginning, and is still present in the checkpoints. So automatically the reservoir version is the commit version, and the index is the zero-based position of the file. So as you can see here, we are not processing the whole scope, the transactional scope, but we really take the number of file. And the last legacy term is the starting version, sorry. In the base code, you will see that it's called is snapshot version, something like that. And it refers to how you start your query. So when you don't define any starting version or any starting timestamp, this value will be false. So when automatically will take the snapshot table, so the most recent version, and when you define the time travel, when you do the time travel, this property will be set to true. And that's not unfortunately that easy every time. There are some tricky points, like in-place operation and schema changes, and I have some demos to show you that. So the in-place changes are the updates your provider or data provider can perform on the table, and unfortunately, if you don't define skip commits, let me show you the property. When you don't define skip change commits, your query will unfortunately fail. And I will demonstrate it right now. But it will fail only when the change happens after, because I have another demo when there are some delays before starting the query, and in that case, query performs runs correctly. But as I said before, since there is no time travel here in this delayed version, you only get all the records that are present at the table after the delayed. So that's already something regarding this snapshot difference I mentioned before, and now we are seeing the demo for the update running. So as you can see here, we are creating a simple table, and once the stream started, there is the data provider who performs an update on a letter. And yeah, it should fail anytime soon. Generating data. Okay, yeah. Don't let me down. Accelerate a bit. Okay, so we have the first microbatch that started and printed the table as it was created in the beginning. And now let's suppose that the provider made some changes, some in-place changes in the table, and you can see that we have this failure with some hints already, which is nice. In kind of all errors I encountered with that, there are always been hints for the solution. So here you can see that it's suggested to use this skip change commit, or you can start with fresh checkpoint directory. So with that, you will get this snapshot version of the table. So remember, always it's important to keep in mind. There are also other solutions, but this one requires some effort on the data producer side. Like you can ask the data producer to enable the change data feed, and in that case, when you stream the change data feed, you will be able to get the very low-level details about the operations, like what was deleted, the deleted row inserted, and before and after update row versions.
And there is another one, so that's you can also ask your producer to define the delta table as an append only. So here you will typically retrieve the semantic of Apache Kafka. But again, it's the matter of communication. You must agree with your data provider to do that, and it involves that the data provider will not be able to do any updates. So it will be always an insert that will need to be interpreted by you and by other customers as an update or as an insert or as a delete. So it's a little bit tricky as well. And there are also other properties, but I will not spend much time on them. There is a GitHub repo already for this repo is publicly available, so if you want to take a look, README, I think README is explaining pretty well all the ins and outs. And I will move on to the writer part. So the writer part is a little bit easier compared to the reader. It takes the same logic like any file-based writing, besides this commit metadata file creation. So you configure the max records per file, the task writes one or more files, and each time a file is created, the information goes to the tracker, add files tracker, and once all tasks complete, there is the commit log creation action with all these add files generated. And later, if the commit succeeds, the job succeeds too. Otherwise, it fails. So it's relatively easy, but there are also some gotchas. Schema changes again, but Scott will explain them way much better. And there are two other tricky things like fan-out pattern and partial success and retries and orphan files. I have demos for both, but I will show just the first one for the Idempotent writer. And the demo is here. So I'm using the for each batch. And when you write some delta table with this method, the fan-out pattern is when you want to write into multiple places from the single data frame with maybe slightly little changes in the input data set. And if you want these writes to be idempotent, so to occur only once, you need to define the transaction version, transaction AP ID. And it can change because if it changes, Spark will consider it as a new commit and it will create new files on your storage. So to demonstrate it, there are files for idempotent. There is not idempotent generation. I will show the idempotent one.
Idempotent one starts with the failed run. So we configure
writer as idempotent and we set the flag to fail. And there normally this operation will only write to the first table. And later there is, let's suppose that it was a runtime issue. We deployed a new version of the job and now the second write will succeed. And after that, I will check whether the fan-out checker detects some duplicated entries or not. So let me just run because it might be slow. But the good news, I'm not running out of time, so Scott will have plenty of time to explain this great schema evolution board. And I can see that my camera is broken, so let's continue like that and see what happens. So there is the writing for both tables. Yes, and the failure should happen very soon. Okay, you can see that we have our exception. And now let's run the same code, but with the idempotency. Sorry, without the error.
While it's running, I will show you when you can find this
information about the transactions. So it's in the commit log in this transaction part. And if I'm not mistaken, there is also an entry in the log, in the Spark logs, saying that this given write will be skipped. Okay, yeah. So
the write source, so that's why there are multiple writes. I will maybe stop right now after the first one. And
error around the fan of checker. That is a sample grouping query by possibly duplicated values, so timestamp and a value, and filtering on the count for the groups. Normally, both outputs should be empty, but let's see whether the gods of demo will be treating me fairly or not, because it was working on my machine outside the demo. So
sorry for the sound, by the way. That's maybe my
oldish piece Linux machine. So you already see that there is no duplicated entries, even for the failed table write to the table location 1. And okay, so I'm meeting the retrace and orphan files to leave the floor to Scott, but you must be aware that any failure may left some files that are not associated with any commit log. And as a result, is yet another reason to run vacuums quite often. And over to you, Scott. Thank you, guys. Sorry for the video. I see that just now that it failed, but I think that the code was more important than my face. And I let you share your screen, Scott.
All right. Let's go. All right. Let me go do this. All right. So let me go back over here. Blah, 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 present. All right. Okay. Hopefully everyone can hear me. Okay. Thank Bartos for going through all of that other all the other side of like the streaming from like the actual like data stream readers and data stream writers and the fun of like the configurations and everything else there as well. It's interesting for I think for people who, if you haven't gotten into like Delta Lake streaming yet, but you're coming from like, you know, kind of traditional like Spark structured streaming, not a lot of stuff is different. I think for most people who are using like the, you know, Kafka sources and everything else like that, it just becomes easier. So Bartos, to your point before of like you don't have to sit there and have like this gigantic metadata that's all like, you know, offsets and fetches and positions and everything else in your commit log. It's just like version 1, version 2, version 3, version 4. It's much easier to do a lot of stuff like with Delta Lake. And you can also treat it in the same way that you would Kafka and stream. And in a lot of cases, it ends up being a lot faster than Kafka because it's already been written somewhere and you don't have to then stream everything over again. We've seen like incredible kind of throughput rates. And anyways, I'll move on from there. So the second part of this is basically from simple, which isn't simple, but it's kind of funny because like the everything that's being done for Delta Lake streaming is not simple. It's simple with the APIs, but it's very complex behind the scenes. But when it comes to kind of like schema enforcement controls, like how people use the data, like what the truths and invariants and promises are for people who are using your data or working with your data, who trust you to do their job, Delta Lake can literally be like a saving grace for all of that. So we're going from simple, which isn't simple, to complex, which isn't simple. It's very complex. And a lot of it ends up being just basically people. So like in the spirit of like Spark and working backwards, like what's complex is basically people expectations, constraints, then schemas. Schemas are easy to understand. Constraints are not as easy to understand. People's expectations are really hard to understand because sometimes they're subjective. Schemas are objective. We can talk about that later. All right. So people and expectations from simple to complex. So people build and they support our data pipelines. I write data pipelines. Bartos writes data pipelines. Everybody who's probably watching this either writes data pipelines, wants to write data pipelines, or is using like basically the data that's like the output of those pipelines. And so people end up being like the biggest kind of barrier to entry to the success in a lot of like data projects in general. But if we find ways of working with people really well, then everything gets a lot easier. So these are just kind of like life points, I guess, right now as we get into schema enforcement. So data pipelines support data products. So if a data product is like the end result of a lot of transformations and the work of many pipelines that are all working as like a symbiotic system, then we have a bunch of things that are happening. And then we have, our golden tables, whatever else, like the output of all of our streaming pipelines generates. So if people don't have to think about like the internals of how everything actually works within the pipelines, like if you think about like what's an internal need to know versus what's like external, we're going to cover that a little bit later when we go through a little bit of the Medallion architecture for data quality. So I guess to recap, right? Sorry, I'm like, there's like changes in between the Google slide, but people build and support our data pipelines. And data pipelines support our data products. And data products are collections of tables and other data assets that help us do our job. So trust is required for us to basically grow from like 1 table to 2 tables to 5 tables to less than 10 tables, and from 10 tables to 100 tables. And after 100 tables, things get really, really complex and people usually start to fight and things break down. It becomes like more like war. And we don't want that. We want to have like a nice friendly exchange like between teams and everything else like that. And so with that, that's like where like the invariance and expectations come into play. And so if you've used just kind of regular Parquet, if you're using not Delta, if you don't have multi-version concurrency control, if somebody wants to update a table, you get underscore temporary. And then everything breaks and you hate them and you don't want that. So instead of having underscore temporary, you instead just get a new version of the table. And so Delta Lake actually helps people be happy, which is a nice thing, especially when a lot of data engineers are, sitting in the trenches hoping to like not get paged during like a holiday weekend or anything else like that. So let's do the nice thing, the right thing for everybody else. So I always kind of pose this question. So it's like, do you expect the best from any of like, from any given data set? Like if it's a new data set, you've never touched it before, you don't know who the team is who created it, like what are those expectations? And like in a lot of cases, like you might have bad expectations based on like, poor behavior in the past, anything else like that. And so like a lot of times it's kind of like this, there's like detective work to figure out how something works. Is it still being updated? Is there an owner? Does anyone actually own it? Will they continue to own it? Is it reluctant, like for that ownership? And there's a lot of things that like are kind of, they add stress to people's life. And so like for me, like there's this sort of joke, and I'm just going to go play the GIF and see if it works. But there's this joke where it's like, every time you get a brand new data set and you've never used it before, and it's kind of like a gift. And if you open up the gift and it's bees, it's not that nice because bees sting and it hurts and it causes problems. And anyways, this GIF used to play when I worked at Twilio. Whenever people would get paged, like the bees would start showing, because at least it's funny, but then you're getting paged. And so while we don't want to look under our seats and get the gift of bees, we want to actually have the gift of like data that actually works. So it's like in order to establish high trust, we need to actually establish a way to measure what trust is. Like, how do people trust that your data is good? How do people trust that your team is doing things appropriately? How do they trust that, like, just in general, so that there's not as much kind of like, questions and answer sessions if you're, going to work with a new data set. Like, it shouldn't take you a month or 6 months to go and, start to use new data. It should take you less than an hour. And it should take less than an hour if like you have like, a high trust environment. Everything else is set up the way that it should. Governance we're not talking about in this session, but let's just say that governance and everything else is there and for the right reasons. So how do we do these things in a unified way? And so we do that just like with simple things. So we have like, so the Delta Lake Definitive Guide, like V2 is out in early release right now. And we have a lot of like kind of best patterns and other kind of food for thought that are out in like the first 6 chapters that are available right now. And a lot of that is just like how to do things like appropriately, but also like, how do you utilize the things that are available to you, including like the metadata of your table. And it's like, these are the things where it's like, if we want to do streaming, we have to do batch first. If we want to do batch right, we also have to make sure that the metadata for our tables is there and it's correct. If everything is correct and in working order, then streaming becomes super simple. But streaming is like one of those things where it's like there's like a high bar to get there because things can never break. It needs to run forever. So there's a lot of kind of like prior expectations that need to be met before we get to streaming anyways. And so like, what's the purpose of a table? Like, do we have useful column level comments and metadata? Like, do we have like that descriptive information about, the table with using table properties? So Delta Lake has table properties that help your utility functions to work. Helps us to like, generate like, compaction files and things like that are specific to like, byte sizes, megabytes, gigabytes. Whether we want to have the append only table like Bartosz was talking about before, but also the table properties can be used like for your own nomenclature as well. And so we talk about that in the book as well. But so if I have a like descriptive metadata, I've got a new table, like my table has like a catalog schema name, there's a purpose of a table. I've got columns. The columns themselves are just a struct type. A struct type has metadata that can store a comment. It has a bunch of other information that's there. It's type safe. Like type safety is a big thing. If you've worked with CSV files, that sucks. If you've worked with JSON files, it can be all right, but it also sucks. Like if you worked with just Parquet and then people have reordered it and then things get corrupt, that also sucks. But like if you don't have to worry about any of that, that's much better. But also like if you have other things that you need to get to that you can just get to from like describe extended with your table or from like the Delta table details. Like what is a team name? If you're using Unity Catalog or anything else, like you're going to have like an owner. But if you don't have that and you're just using open source, you can still do the same stuff just by adding table properties. So like, what's the team name for that owner? Who are they? In this case, it's DLDG authors, but that's just for the authors for like these like use cases. But do you have a Slack channel? Is that Slack channel like something that people will respond to? Like, I don't know if people use email, but is there an email channel? Like, are there classifications and things that will help people to automate things? And like, this is just simple, a simple description of a table that doesn't exist that has, there's no real structure to it, but that's fine. So if we have a table that has good, good metadata and everything else like that, what else can we use, right? In a lot of cases, say we are using partitioning or we're doing like cluster by, like it's really nice to have their partitioning and everything else done directly in the actual like DDL for your table. You don't have to then worry about doing anything else in like your Spark structured streaming code. You don't have to worry about partition by, because it will automatically be done for you on behalf of you by Delta Lake. So if I have a generated column, that's great because I fail as a human. We all probably fail as humans as well. And like, it's like, well, I can't guarantee that I'm going to remember to do the right thing. But if the table does it for me, then that's even better because I can be lazy. And then also like there's other things too, like while we can automatically merge any change that comes into our table using like merge schema true, we can also overwrite schemas. We can also overwrite tables, but like there's the cost of side effects. And we don't really want the side effects to be something that cause pain or suffering for people who are downstream to our changes. It's really nice that we can do these things, but a lot of times we shouldn't do them unless we know how to use them. And so we'll get to that other stuff later. We'll start off with the generated columns. So if I have a new table, or if I want to basically like replace a table, and I want to add a bunch of cool columns, a nice thing in like the Delta table builder library. So this one is just like the PySpark version. So Delta tables, import Delta table. I can add all columns. And if I want to add all columns, I can just give it like my data frame schema. So it just takes a struct type. So if you've sat there and you have a very complex, actual table that has some nesting and everything else in it, it's a pain to sit there and traverse the entire struct to go and do everything. But if you know what you want and you're doing things correctly, at least for your first version of your table, you can define everything else you would using normal transformations, then just steal that schema, toss in the table definition, create your table, and then you can write. So in that case, at least you get like, it's two actions, right? I'm going to go and create my table, and then I'm going to go write to it. So if the table doesn't exist, awesome. If not, whatever, it's a no-op. It doesn't really matter in this case. It would just skip it and move on. But the cool thing is over here, like if we have, say, like an ingestion date column, and we have a timestamp column, and we want to do basically a casting from our timestamp to a date, and then we want to partition by our date, we never have to do partition by at that point. It just automatically will partition for us, which is really cool. Just remember that partitions can also create small files, and that can cause big problems. All right. Like I'm probably doing good on time, just racing through stuff. All right. So ways of working. We've talked about Medallion architecture. We haven't talked much about streaming Medallion architecture. So Bartosz, you brought up a lot about like how things stream and how things kind of flow into the system, whether it's coming in from Flink, whether it's coming in from Kafka, whether it's coming in from like a file stream source, from S3 or blob storage, etc. In this case, I just have a diagram that I had already created, so we'll just use that. It's coming from Kafka. So we have Kafka data, and it's feeding into an application, and that's feeding into like our bronze level tables. Like we have this notion of like an internal data domain and an external data domain. Internal data domains are basically for people on your team or people that are like within like your data domain who kind of need to know more of the lower level information, like, or have access to like really raw data that no one else should have. If you give everyone access to raw data, then you're never going to be able to update it and you're going to always support it forever. Or you can treat everything more like an API where you have essentially transformations and changes from raw. You can basically change different sources, and all that stuff happens as more of a kind of a black box that no one thinks about. Externally, everyone just stays happy. So like they have an API type contract and everything else just continues to flow as normal. They just never have to know about it. Like if things change or if you're doing replays or if something broke, it's like, well, it's delayed and degraded, but at least it's degraded and you don't have to worry about now fixing all your stuff. And so there's all these things that can happen internal to anything anybody else has to know about, which is really cool. And so this is kind of like the streaming medallion architecture where everything's still streaming. It's still being orchestrated. It's still using the transaction log from Delta to be able to push new commits as they're available. And the other cool thing, like with Delta, if I have a streaming application and I'm waiting for new data, if I'm not using available now, say I'm using process time and I'm just waiting every 10 seconds to go check on, do I have new data or not? Hitting the transaction log is just metadata. If there's nothing new, cool. Doesn't really matter. It's like a very cheap operation. Doesn't take a lot of like compute or anything else to do that. If you want to use available now processing, we can talk about that in a different talk because we're going to run out of time if we start talking about that right now. But there's a lot of interesting ways of orchestrating all these patterns depending on like the speed of which your application actually has to produce data. Sometimes we don't have to produce data as fast as we think we do, but we want to get all the benefits of like the streaming, statelessness. Like I want to be able to basically not ever worry about like where my application's running. I want it to run, and I never want to think about, managing state myself. There's a lot of reasons why streaming ends up being a better use case for a lot of people as well. It also makes you think about your applications differently because you want it to be able to run in any mode, which is cool. All right. So anyways, very quick primer, Medallion architecture, very raw data. Could be essentially like no different than just like, raw Kafka data, key, value, timestamp, topic, partition, blah, bytes. No one has to ever think about it. Transformation into an actual type that sits in Silver, any other kind of transforms, anything that no one has to worry about. And then when it's published, it's essentially something that people can actually use. And we can kind of talk about that stuff later, or we don't have to talk about it at all. We cover it in the book under the Medallion architecture. But yeah, I guess that now it's there. So lean into it. All right. Moving on. Sorry. The order in which the things are animating is funny. So putting everything else together, we just kind of sort of talked about. It's like people make data pipelines make data products. Apple's like thumbs up, and then data products also end up generating the things that we need to get our jobs done. And so if we get our jobs done well, that's awesome. But also sometimes if we're doing our jobs well and we're rushing, then we're going to cause problems, even if we are thinking about doing things the right way. And that's where like the schema conformance and evolution and everything else kind of comes into play. So Bartos talked about the schema before and like tracking schema changes and being able to understand like when things actually, are they divergent? Are they broken? Are you ignoring changes, etc.? So in this case, if I have like, let's say we have a data frame that has information in it. All those code samples, they're available. There's links at the very end. This is part of like the Hitchhiker's Guide to Delta Lake Streaming, which was like a talk last year at like Data AI Summit. But let's say we have something where it's like, let's break stuff. We have a result, which is basically coming from our own table. We're like, cool, let's be sneaky, add a new table, like add a new column, and like, let's just go and write it. Let's sneak this in. No one will ever know about it. That's completely fine. The cool thing is like, if we go and do things the wrong way, but we overwrite and do, sorry, my thumbs up keeps showing up. So thank you, Apple, again for that. It is a good thing. It's a good thing that we have ways of not being sneaky as well. But so if I try and overwrite the schema, that's awesome. If I have tried to overwrite the schema, but I'm also creating problems because the schema doesn't like, doesn't actually still have all like the same values or anything else in it, I'll at least have like basically a diff. So what was the table expectation? So if we think about this as like Delta Lake has the Delta log and Delta log has the current version of the schema. Locally, I have my snapshot that Bartosz was talking about. As we actually, we'll build a snapshot. That's our starting version. So when we go to write, we have an expectation locally, and then Delta has an expectation at the server side. And there's nothing we have to do other than say, I think it's like this. And Delta says, no, you're wrong because I've seen changes that are different. Then we go, oh, I'm sorry. We've got an analysis exception. And this is like this in itself, if we take nothing else out of this part of this whole entire talk, it's that just having the ability to run this diff saves you so much pain and suffering, just like that. So in this case, our root schema, like for the table, has different values. It doesn't expect the category ID and event type column. If we want to go overwrite it, then it tells us what we could do. We could overwrite our schema and do this other stuff, but also we shouldn't overwrite the schema if there's other ways of doing it. So if we want to opt into changes, we can treat things like we would kind of a typical like relational database, right? I'm going to go and alter this table. I'm going to add this column. It has a type. It could have a default type. It could do a bunch of other stuff. Like it could have constraints. That's fine. But we want to like manually opt into it and say, okay, I don't know if I can trust what's coming in. A change is happening. Let's make sure this is happening for the right reasons. And so if we turn off all of like automatic schema merging or anything else like that, then at least we break for the right reasons if our expectations of what we're getting from our upstream changes. So we can be safe, and that's great. Otherwise, if we trust our upstream because we're like, okay, cool, like it's a high trust environment, they've never, done things that we don't expect, and we actually need the new data that's flowing in, then we can automatically pick it up. But if we don't need the data, then we don't need to actually pick it up, and we could also ignore things as well. So it's kind of just being conscious of the things that are happening. But if we do want, I'm like, I don't have a pointer. So if I do merge, merge shame, this was, it says schema. Promise it's not a typo. So merge schema with an E right here. Anyways, this totally works. Trust me. So if I merge schema true, that'll end up allowing me to go and do like these overwrites as well. So we can automatically accept these changes. All right. So demo time. I don't know, Bartosz, I think you're using that, a cool thing for like the switching between. Let me just go and switch to Jupyter Notebook, blah, over here. All right. Cool. So this thing actually should run. It's always like the end of like my demo whenever I'm like, it's going to run, and then it doesn't run because sometimes things never run. So running. This one has this thing, so that's good. So if we do like the let's break stuff, that's awesome. So we add a column, we do all this other stuff. If we haven't committed anything else back, we'll see, okay, we've got this category event ID. This is basically doing like a hash of some columns because we think we need it for some reason. That's cool. So if we want to go and actually try and merge this, in this case, we don't have merge schema with an A because that was, and it doesn't matter from the presentation. But so if we were to say, okay, let's break stuff, let's drop product ID because I don't know why we would need a product ID even though it's e-commerce data, which is from like a Kaggle data set. But let's break stuff, drop product, let's write to Delta, let's overwrite, and let's partition by event date, and then let's write out to our table path, and let's go save it. Like, okay, we're trying to basically change some stuff, but luckily we get into like it's like, hey, did you think about this? Was this the right thing to do? If it's not the right thing to do, then cool. At least and if you want to change it, you can go back and change it. But like if you're not running in a notebook environment and you've actually gone and released a pipeline and then it fails, that's great because it allows you to make a change and push a change. And you're like, okay, I really want this change to happen. So then you can either do the alter table or just opt into the change that you expect to happen. But it makes it so it's a lot harder to basically like sneak things in or to break things by accident. Even if it's like you doing like, underscore first name, capital first name, first underscore name, like all these things that like would change to just create new columns that are stupid. Like, let's be cool and ensure that the things that we do matter. So I already talked about this. got dyslexia, so let's just move that over there. So merge schema would have worked better that way, so that's great. All right, so before I had changed that and took pictures, we essentially have a delta log history, and we have write operations. So this one was an overwrite with partitions. That's great. Merge schema is also additive, which is interesting. So if I go and I try and drop like a column, like say I try, like in this case, I'm like, you know what? I think I really needed to go drop product ID. I don't need it. I can go and drop product ID, but product ID doesn't leave the schema, even though I said drop it and then overwrite my schema. Like I'm just gonna, I don't use overwrite, I should say. I just use merge schema. Then I'm going to keep my column. So product ID is null. So can you spot the null mistake? We made it right here. That's cool. So we drop product ID. It's not great, but let's get it back. So in this case, if we go back and we take a look at like what we did, we were adding columns. We also did like our overwrite. And then if we want to go and restore, which I've already done and run this again, so that it's not as cool. I buried deleted a little bit, but so if I take a look at the history and I say, okay, I wanted to restore to version 14 because version 14 was where like I made a mistake. And then over here, I can then go take a look at what I had done. And if I use time travel, I get my product ID back, which is great. So even if we haven't schema enforcement and we accidentally like make a breaking change, that's all right. We don't have to worry about that. We can restore it, no harm, no foul. And then this is the part that I had promised, and then Bartosz reminded me this morning. If we overwrite the table schema by accident, because we're like, you know what, forget it, throw caution to the wind. We just want this thing to happen. It's going to go out. We might break stuff. We don't really care. Then we can. So we can basically take this is basically a delta table reference. I'm converting it to a data frame. I'm dropping the category ID event type column, which I added, which wasn't useful for any reason. Then I am going to overwrite everything, including the schema, just to basically trash that column. That's great. I can go save that. Awesome. The big thing is that if I go and actually save that, it's going to, in the case where I change, say, partitioning or anything else, it will take the entire table and it'll read the table and it will rewrite a new directory layout. So if you have downstream consumers who are streaming from your table, they're going to get very mad at you because what they expected no longer works, and now their streaming pipelines are broken. So if that happens and you're like, oh, well, we screwed that stuff up. We didn't mean to actually do this like this overwrite, et cetera. And we want to go back to a version that was actually normal, then we can still do that. So even if we overwrite the whole table, we can still go back to the prior version as long as we actually haven't vacuumed the table. So if we have, then we're screwed and that's okay. But if we made a quick mistake, we should never do it again. But we can restore that. And then in that case, like we get like our product ID, and we even get like this column that we didn't need back because we restored it. All right, so there's that part. And then I'll just wrap up on this other thing over here. So that was the promise of the overwrites. So like time-wise, I'm running out of time. So I will give this back to us in just 1 minute. So common reason for table overwrite was like we created a delta table, say without any partitioning, and now the table has grown over 1 terabyte. So action needed to be taken. And so in that case, this is like the example that I was showing in the Jupyter notebook, but like we can always make a change. In this case, like if we wanted to add a new partition column, say by event date, and we wanted to go and drop the other column that we didn't need, we can go and do all of that stuff. We can restore the actual like, prior layout of a table, or we can add a new layout to the table. And then we save it, everything else will be done. And then you can still time travel to go back. And that's pretty much that part. And so let me just stop sharing and I can open the floor back up as well. It's a lot of cool stuff there. Schemas and things.
Awesome. Thank you both. Excellent presentation. And we have some questions here from the community. So we will transition now into the last 10 minutes of questions. So one of the questions we received here, is it a good idea to write to 2 delta tables in a single streaming query, or should we run 2 Spark streaming queries?
Alice, you want to take that?
Yeah, well, it depends. I would say it depends on what we are expecting to do. If the writes are decoupled somehow, if the failure of the second can break the first one and you don't have any latency concerns, yeah, it's simpler to do, simpler approach, you can go for it. But if both should work in isolation, so when one fails, one failure shouldn't impact the others, well, it's better to have them isolated. That's, for me, the easy way to distinguish whether it's best practice or not. If Scott, if you want to complete, yeah, feel free.
Oh yeah, I mean, I think, I mean, along those lines as well. Like I think it depends to, like, if you think about like Medallion architecture, if people are streaming off of like the end results of like things that are being like published out of like the internal data domain, a lot of the things that would be like needed to be like, if you're reading from raw and doing all these transformations across a bunch of different pipelines, it'd be a lot more costly if one thing went wrong. And so if it's inexpensive to go and like, you know, read like an incremental change, to go and write out to 2 or more sources, then that's completely fine as well. But we've also seen like that issue too, like if you have different kind of joins and everything else like that on tables that aren't ready and things break, like left join type stuff where you're just sitting there kind of frozen in place. If you are blocking other stuff, then your pager goes off. And so it really is like, to your point, Bartosz, like there's not like a good silver bullet for a lot of the stuff. It's like, you know, it's what is it that makes the most sense for like the SLAs. And if there's no SLAs, then that's cool because you can take as long as you want. But if you have a really high priority stream, then you should just treat it with the respect it needs.
Awesome. Okay. Hope that answers your question. We have another one here. Is there a good practice to backfill data in the streaming table when schema changes?
Alice, do you want to go?
Let's start this time. Scott, start it.
Okay. I'm like, I have like, I don't know, I've got like terrible advice for a lot of stuff. So like, I think with backfill, like, if you want to backfill because the schema changed, like, are you backfilling because like the schema like is destroyed and it's corrupt? Or like, are you backfilling because like you're now adding a column that you wanted to have that wasn't there before? Like in some cases, like it makes sense to go back and like refill, you know, rehydrate like the last like 2 years of something. In a lot of cases, no one's going to ever need it. So really, it's really dependent again on like that use case. Like, for example, if you haven't opted into schema changes and you're ignoring changes like in your streaming query, and say there's like 10 new columns that you had no idea existed because you just didn't ever need them. Like technically you could go back to the version where those changes started to occur. You could find that and you could rehydrate that as a separate, you know, you could overwrite a bunch of stuff. But is the impact to overwrite more expensive? Like in the long term, could that cause more problems? Like, could that cause more problems as well? Like, there's that whole like Yagni method where it's like, you ain't going to need it. And if you don't need it, then you shouldn't do anything with it. But if you do need it, then you can always sidecar it and overwrite. Like there's specific like replace where conditions. And if you can do a replace where on a table by doing the backfill, then at least you're only making changes where people might need to get to those new changes. But otherwise, I consider it kind of like if you needed it and you didn't have it and you need to do a backfill, you sort of kind of corrupted your downstreams. So it might be a communication issue too between teams. Like we're making a change and then no one knows about it.
Excellent. Thank you for that. We have a question here. Apache Kafka compared to Spark. Kafka compared to Spark, structured streaming and Delta streaming. How does it compare to Spark?
Bartosz, this is you.
Yeah, I think that the question is more a comparison for Delta Lake and Apache Kafka, because Spark is just running them. And I think it's more on the semantics of the data stores. When you write data tables and you want to process the data, you can process it as soon as the combi log is not created. So automatically, the first row will be created when the last one is written, so kind of. Whereas in Kafka, it's more continuous. So whenever the producer writes first row, it's already available for processing. There are similar concepts in Spark, like with these offsets that are present in both sides. There's first positions and positions. You can limit the throughput. I think there are some nice features for Kafka and Spark that you can consume one partition from both ends or from multiple tasks in Spark to go faster if you don't have any combinational constraints, for example. So there is a good things on one and good things on another. Both on Kafka, for example, you don't have the same schema controls as on Delta Lake. So yeah, I don't know what to answer, but technically they are different. Yeah, maybe Scott, you have something else to add.
No, I think it's a good thing, right? It's like apples to dogs. Like there's different, like there's completely like different things like Kafka, Pulsar, anything else where it's basically like, in a lot of cases it's being used for exponential backup, but it's also being used so you can rewrite in the case that things go wrong. You can read the same data off of Kafka from Spark, from Flink, from anything else like that. And then you can convert all that data into Delta Lake as well. So really it's just us taking a look at like, here's a protocol stream that's doing something. We're reading it from some sort of stream, like compute or stream processing framework. And then we're writing a different protocol like out, but all it's the same thing, right? Like, we've got a lot of times row-based data. So we've got like Avro, we've got protobuf, we've got et cetera coming in. That gets dumped into like some sort of file system. That's great. And then we basically switch it into like a column or format like Parquet, and then like, Delta wraps Parquet and adds, simplicity functions on top of that to allow us to, reorder columns and do things that aren't available like in Parquet. And so it's all just like shades of gray for a lot of this stuff.
Excellent. I think we have time for one more question. Is streaming always unbounded, or can it be bounded too based on micro batching?
Bartosz, you want to take it?
For me, it's still unbounded. I don't know how to interpret the boundedness in terms of microbatch. Yes, I don't know if you got the question, but in one sense, it's bounded in terms of microbatch because you take one part which has an end, but typically streaming is there to be unbounded, to be continuously growing. You should continuously processing new data. So I'm not sure if I get the question, but maybe Scott, you have some highlights, more highlights than me.
No, your question's right. It's like an assembly line kind of like if the conveyor belt's always moving and things are like flowing from left to right or wherever direction however we think in terms of directionality. We're only looking at things in terms of like what fits within like, some sort of threshold. So if it's, max bytes per trigger, or if it's max files per trigger or anything else like that, we're going to only pick up the amount that we can handle. And then we're going to process all of that. And then we're going to write it and commit, and we're going to start again. And that system is going to go forever versus us looking at more of like a tuple stream where we're taking a look at every individual record like we would with continuous mode processing. And so it's unbounded, but it's bounded in the way that you process it. And it's usually only used because you want to group things together and you want to be able to benefit taking a look at, iterative processing over a lot of data at the same time as well.
Awesome. Well, we have a lot more questions, but not a lot of time. So unfortunately, we are going to have to end today's Delta Lake deep dive. Maybe we need a part 2. It seems like there are a lot of streaming questions out there. There's another thumbs up from Scott. So awesome. I want to thank today's speakers, Scott Bartosz. I appreciate you both coming here, educating the community on streaming, and thank you to our wonderful attendees. Awesome questions. We can follow up with the full recording on YouTube. You will be able to rewatch today's session. And with that, thank you and have a great rest of your week, everyone.
Bye, everyone.
Bye-bye.